Welcome back, and we have one more example here. It is going to be along the same lines as the first one, so we have to do all those sorts of things as we did in the last video. So the only thing we don't have to find, it doesn't say to find any roots, so we don't have to do that. But nevertheless, let's get going. So first thing before we really get going, I want to just recognize that the domain here is restricted from all real numbers, right? Because of the square root, we are just on a domain that is -3 inclusive to infinity. And we can actually find the zeros of all this as well. We can say that the zeros, or the roots, even though it isn't called for, is going to be when is at x is equal to 0 and x is equal to -3. -3. Okay. And so now we have to go through find intervals of increase to decrease, max and mins, intervals of concavity, points of inflection, all that good stuff, and generate the graph. All right, so without further ado, let's go on. So I want to look at the first derivative, which we do have to do the product rule, right? At 1d2 plus 2d1, all that good stuff. And I'm just going to say you can do that. You're very good at that by now. And when you simplify it, you end up getting, if you factor it out nicely, it's going to be x plus 3 to the minus half, and then times the quantity, 3 halves x plus 3. Okay, you might have to do a little bit of algebraic manipulation to get there, but you will get there. Okay, and nevertheless, if you set this equal to 0, okay, then what this is going to give you are the critical numbers that are x is equal to -2 only. Okay, effectively, since this is in the denominator, it doesn't yield any critical numbers, but we do get critical numbers from that first part. Okay, and so when we use that critical number to make our sign charts, okay, f prime and f, okay, we do -2 there, and then we want to take sample values, so like -3, and f prime is 0, okay? And what we're going to get here is a negative number here, and actually remember the domain is only from -3 and over, okay? So I should probably do something more like -2.5, just so that we're satisfying the domain restriction, okay? Or we're taking a true test value, I should say, not just a boundary value. Okay, and when we do f prime of 0, right, well, we should just get a positive number. So that means we're decreasing here and increasing there. Okay, and then so consequently we have, if I'm making a list of things, I have, the intervals of increasing being from -2 off to infinity, and it's decreasing from -3 to -2, and I'm still using parentheses because, again, we can't say it's increasing or decreasing at a single point. And I also have a local min at x is equal to -2. Okay? So that's one thing down. Okay, so let's just review the problem. I have found the intervals of increase, decrease, max, and min values. Okay, and now I need to tackle concavity. Okay, so concavity is the second derivative, and again, you're welcome to do this on your own. But the second derivative, if you've simplified it, ends up giving you x plus 3 to the -3 halves times 3x plus 15 over 2. Okay, and so if you set this equal to 0, your potential point of inflection, you'd have to verify this, would occur at x is equal to -5 halves. And so if we make a sign chart again for the second derivative this time, we would look, okay, so we still have that boundary of -3, and then we look at this -5 halves area, and here I'll tell you, if you do like the second derivative of -2.75, you end up getting a negative value, meaning that it's concave down here, and then here if you do, second derivative at 0, you're going to end up with positives here, meaning that's concave up. Okay, so this is indeed a point of inflection. So I'm just going to make note here that it's concave down on -3 to -5 halves, concave up on -5 halves to infinity, and then we have our point of inflection at x is equal to -5 halves. Okay, now again, this is a point I should really find the y value and specify it, but I'm going to just press on with this. Okay, and now what I want to do is use all this information I've acquired, right, all this increasing, decreasing stuff along with the domain and zeros to graph the function. Okay, so let me just get my screen positioned correctly here, and I'll do it off to the right. If I do that, okay, so 1, 2, 3. Okay, so I know it has zeros at -3 and 0. Okay, and I know it's increasing from -2 to infinity, decreasing from -3 to -2. So I know it's doing something like this, and the concavity is the other interesting. So it's actually concave down until about there, and then it switches concavity there, and then increases slowly. Oops, undo that. Undo. Something like that. Okay, so there I can see, maybe I need to make this a little bit more pronounced and do your best to imitate this on your sketch. But there would be my local min. There it changes concavity, so it's concave down to concave up. I have the zeros on there, I have the domain reflected, and it's increasing and decreasing the respective places. So this seems to be a pretty good sketch of the graph, okay? And you can always compare it to Desmos if you have those resources available to you, but you should not use them to get the graph and just replicate it without all these facts, okay? So that's one more example, and you'll get many more examples as you go through these in class and in your homework.